everyone, and welcome back to Neuropsychology. So in the last video, we talked about the membrane resting potential. We also talked about concentration gradient and voltage gradients, and we talked about graded potential. So if you remember, you had the hyperpolarization where the inside of the cell becomes a little bit more negative compared to the outside of the cell. And we had the depolarization where the inside of the cell becomes a little less negative, so a little bit more positive compared to outside of the cell. And don't forget this figure. So this is at rest whenever the cell is at rest. This is an axon. So at rest, the concentration of sodium and chloride is larger outside of the axon, outside of the cell, whereas the concentration of potassium and protein and ions are larger inside of the cell. So in this video, we will talk about the action potential. We will also talk about voltage-sensitive ion channels. We will talk about the phases of an action potential, how the message goes along the axon, and saltatory conduction and myelin. Okay. So electrical stimulation of the cell membrane at resting potential produces localized graded potentials. We already talked about this a little bit. So the more stimulation, the larger these graded potentials are. So if there's a little bit of stimulation, these graded potentials will be smaller. So the action potential is a little bit different because the action potential is a brief but extremely large reversal in the polarity of the membrane and lasts about 1 second. So during this, the inside of the cell actually becomes positive compared to the outside of the cell. If you remember from the previous video, the resting membrane potential is negative 70 millivolts. So during an action potential, it becomes a little bit positive. So it becomes positive around like 30 millivolts compared to the outside. So how does an action potential start, right? So to get an action potential, the membrane needs to be depolarized. So it has to become less negative or more positive. So if the membrane potential goes from its resting potential of negative 70 millivolts to negative 50 millivolts, which is the threshold, then whenever that threshold is reached, the action potential will occur. Okay, so one important thing about the action potential is that it is an all or nothing event. So if this threshold of negative 50 millivolts is reached, it will happen. If it's not reached, it will not happen. So that is one big difference between graded potentials and action potentials. It's because graded potentials can be small, they can be large, but action potentials are always similar, and whenever the threshold is reached, they will happen. The whole thing will happen. Okay, so here's a schematic image of the action potential. So the membrane right here is at rest at negative 70 millivolts. So whenever the membrane is depolarized to negative 50 millivolts, which is the threshold, the action potential will happen. So whenever all these graded inputs, which we will talk about later, will make it a little bit less negative, it will go up. And whenever it hits this threshold, the action potential will occur. So the first thing that happens is sodium will go into the cell. So sodium channels will open up and sodium channels will go into the cell. So sodium is positive. So if the inside of the cell becomes more positive, this will go up. So it goes up, 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 up. And then eventually it will reach around positive 30 millivolts. Whenever it hits that, then the membrane potential will reverse, and then a hyperpolarization will occur. So here, the sodium channels will close, there's no more sodium going into the cell, and this is where potassium will start going out of the cell. So potassium is positive and it's going outside of the cell, which means that it is going down, 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 down. Since right now we're at positive 30 millivolts, potassium is going outside of the cell, which will make it more negative. So because potassium channels are a little bit slower, it always overshoots a little bit. So it goes a little bit down too much, and then eventually it will go back to resting membrane potential of negative 70 millivolts. So there are two types of ion channels that I wanted to talk about that are very important for the action potential. So these two ion channels are the voltage sensitive sodium channels and the voltage sensitive potassium channels. So these channels are sensitive to changes in the voltage of the membrane, and they will open and close accordingly. So whenever the membrane is resting or chilling, these channels will be closed. When the axon membrane reaches a threshold voltage of about negative millivolts, the sodium channels will open. So then sodium will go into the cell, and it will make it more positive. So when sodium comes into the cell, it produces a large depolarization, and it will reverse the polarity of the membrane, so that the inside of the membrane is more positive compared to the outside. So when this polarity of the membrane becomes positive, it will stimulate the sodium channels to close, and then the hyperpolarization will happen. So potassium channels open a little bit slower, and then the potassium will go outside of the cell, which again will make it, as you can see right here, it will make it more negative. So because these potassium channels are slower, it will have a little overshoot right here, as I just talked about, and then it goes back to the resting membrane potential. Okay, so sodium and potassium channels are a little bit different. They're different in structure. So here's a picture of it. Here you can see the sodium channels, and here are the potassium channels. So the potassium channels only has one little gate, and the sodium channels have two gates. So for the sodium channels, one is often always open, and the other one is closed. So when the cell reaches threshold voltage of negative 50 millivolts, the closed gate will open, and right after, the other gate will close. So it's only a very brief moment of when the sodium channel is open, but it's enough time for the sodium to go where it needs to go. So then the potassium channels only have one gate, and they are very slow to open, and they also stay open for a little bit longer. So that's why it has a little overshoot at the end. Okay, so there are two phases that are really important during an action potential. So when the axon membrane is stimulated during the depolarization or hyperpolarization phase of this action potential, it does not respond to a new action potential. This is because the sodium gates are insensitive during this period. So whenever an action potential is happening, a new one cannot be induced. So this phase is what we call the absolute refractory period. However, after this phase, this is where the little overshoot happens. If the axon membrane is stimulated during the overshoot, a new action potential could be induced, but only if the intensity of the stimulation is higher than that which initiated the first action potential. So let's look at a picture. So here I have a picture. So here you see the membrane at rest, and then the graded potentials eventually stimulated it enough that it reached the threshold. Then sodium channels open up, and sodium will go into the cell. This makes it positive, so it goes up, 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 gets positive. then the sodium channels will close, the potassium channels will open, and potassium will go outside of the cell, making it more negative. And then here you have the little overshoot, and then it goes back to resting membrane potential. So whenever the sodium channels are open, or whenever this is going down, this part is called the absolute refractory period. So during this part, no action potential can happen ever. During the relative refractory period, an action potential could happen, but only if it was stronger than the previous stimulus. So it has to be really strong for an action potential to happen in this time. There are also chemicals that can block our action potential. So there's this chemical called tetraethylammonium. I know it's a very long word, or TIA for short. And this chemical blocks the potassium channels. So whenever it blocks the potassium channels, it will not allow the potassium to leave the cell, and it will therefore block the hyperpolarization. However, it leaves the sodium channels intact. So then we have another chemical, which is called tetrodotoxin, and this is the opposite. This blocks the sodium channels. So therefore, this will block the depolarization. And a fun fact is that pufferfish they secrete tetrodotoxin. So I know in some countries they eat pufferfish, so they have to be cooked in a special manner so people don't get this toxin in their body. So here is a picture of how they work. So in the top you can see the TIA, and in the bottom you can see the tetrodotoxin. So here you see the TIA, how it blocks the potassium channels and not the sodium channel. So you will still get an influx of sodium. With the tetrodotoxin, it blocks the sodium channels and not the potassium. So the potassium will still go out of the cell, and you will have a little potassium efflux. Okay, so the action potential eventually, whenever it happens for the first time, which happens at the axon hillock, it moves along the axon and it induces nerve impulses. So how does that work, right? So when the action potential happens at point A, let's say point A would be the axon hillock, it goes from negative 70 to about positive 30 millivolts. So that is an increase of around 100 millivolts, right? So this should be large enough to bring adjacent parts of the membrane to their threshold of negative 50 millivolts. So therefore, an action potential will also happen there too. So this will go on and on and on, all the way down of the axon length. So we say that the action potential will propagate another action potential next to it. So it will give rise or give birth to another action potential next to it. So the cool thing about this is that it can only go in one direction. And this is because the previous area that just had their action potential is in the refractory period. So therefore it can only go one way. Okay, so large axons convey nerve impulses pretty quickly. So whenever they're very wide, information processing goes quicker, and smaller axons convey impulses more slowly. So to enhance impulse speed, we have these two cells that we talked about in, I think it was the second video. So you have oligodendria cells and you have Schwann cells. So oligodendria cells are in the central nervous system, and Schwann cells are in the peripheral nervous system. And they make this fatty substance, which they wrap all around the axons of our neurons. So they form an insulating myelin sheath around it. Okay, so this is what that looks like. It's very schematic, but you can see the difference. They have the same function, but they look different. So in the central nervous system, they're called oligodendrocytes or oligodendroglial cells. And here you see the cell body, and here it wraps beautifully around these axons. So these yellow strings are axons. And here, same thing. Here you see a Schwann cell, the cell body, and it also wraps around these axons. So impulses cannot be produced where the myelin is around the axon. So no action potential happens on the location where there's myelin. They technically create a barrier to the flow of electrical current. So the axon still needs to propagate these action potentials, right? So the axon is not completely covered in myelin. There are little parts on the axon that are not insulated, and we call these the nodes of Ranvier. So here you can see the nodes of Ranvier in the PNS. And here you can see some nodes of Ranvier in the CNS. So these nodes of Ranvier have a lot of these voltage-sensitive ion channels that are necessary for these action potentials. So therefore, in these gaps, they're close enough together that an action potential at one node can reach threshold and induce an action potential at the next node or at the adjacent node. So technically, the action potential will, let's say, first happen all the way here, and then it can jump over the myelin and produce an action potential here, and then jump and produce one here. And this is what we call saltatory conduction. Okay, so saltatory conduction greatly increases the speed with which an action potential can travel along the axon. So again, it'll recap. Nodes of Ranvier are uninsulated regions between the myelinated segments, and they have a lot of voltage-sensitive ion channels. Saltatory conduction is jumping of the action potential from one node of Ranvier to the next, and this will increase the rate of transmission of the action potential. So again, there's no action potential where there is myelin, only at the nodes of Ranvier. So here's a schematic image of what saltatory conduction and the propagation of the action potential across the axon looks like. So let's say this is an action potential. Sodium goes into the cell, so it goes up, and then potassium will go out, so it gets less positive. And whenever the action potential happened here, the current flow will go to the next node of Ranvier. Whenever that happened, that will induce or propagate the action potential on the next node. Again, it cannot go back because of the refractory period. So it will keep jumping to the next node and to the next node, etc. So it will have an action potential here, then it will have an action potential here, and then it will have an action potential here. And this will keep going all the way to the end of the axon. So this is the end of the video, and I will see you back for the next video.